Can you hear you? Nope, don't hear anything. Hello? Is it working? Is the microphone working? It's working, good. Okay. So first of all, apologies for making you wait 20 minutes. But blame Apple, not me. So, and I'd like to thank the organizers for inviting me here. It's the first time I've ever been in South America, so it's so far so good. I want to talk to you about this topic on the board, which is about the origin and use of conserved currents and discrete holomorphicity in solvable lattice models. In particular, in this talk, I want to talk mostly about face models, SOS models. So hopefully for people who've heard some of this before, there should be some new stuff here as well in the second half. Okay, so first of all, this is my plan. I want to give a bit of the background, and then I want to go into the details and tell you about the origin of the conserved currents and their connection with discrete holomorphicity. Then I want to say about how to construct these in quantum groups, and then I want to look at two examples. I want to look at the 6 vertex model here, and I also want to look at trigonometric SOS models. And I'll also tell you in the middle a bit about what they're useful for. And this is based on work with these collaborators, Yassin Iklev, Michael Willer, and Paul Zingerstan, in this series of papers. Okay, so the background of all this is that, 2D conformal field theory has been around a long time, since the 80s, and right from the earliest times, there were statements or conjectures about the connection between particular conformal field theories and particular critical lattice models. But they were conjectures. And the first really rigorous results on this came around the year 2000. And there are lots of people associated with that, but the name most associated with it is Stanislav Smirnov. And if you want a review of this, then this is a good place to read. This is from the Congress proceedings in 2010. Anyway, so what this program does is, first of all, it works in a very few cases. So what it does is it looks at the Ising model and a very few other cases which can be related to it in various ways. And it gives a rigorous proof of the scaling limit to a conformal field theory. So typically to a stochastic Lerner evolution problem. And I'm not going to go into any of the detail here, but all these proofs of this scaling limit rely on the existence of a discretely holomorphic lattice operator. And then the idea is that the correlation functions of these lattice models obey a well-defined discrete boundary value problem. And then the flavor of the proof is that the limit of this exists, a scaling limit, and is unique, and it is the conformal field theory. And that's all I'm going to say about this program. So what about beyond Ising? Well, beyond the Ising model, there are a few results, or there were a few results, for operators obeying what I would call half of the discrete holomorphicity conditions. And these were essentially constructed by hand in various lattice models, and the two that were looked at most were the ON model and the ZN model. And it was an understanding that the existence of these half discretely holomorphic operators had something to do with integrability. So you write down a lattice model, you write down a candidate operator, and you can get this thing to obey the discrete holomorphicity conditions in the case when it's integrable. And so what we did in this original work in 2013 was to understand this picture in terms of the underlying quantum group. And it pops out automatically from the quantum group construction of these models then. And that's what I'm going to tell you a bit about, and I'm going to tell you particularly about how it works in SOS models. So this half discrete holomorphicity is only half of the conditions. Nevertheless, by themselves, they are good for something. So Duminil, Copan, and Smirnov were able to prove some rigorous results about the scaling limit of ON models by just using half of these conditions. Okay, so there are some exact results you can get, and also it turns out that these things are useful for identifying the perturbed conformal field theory related to the massive lattice model you start off from. And I'll tell you a little bit about that in the context of the chiral Potts model. Okay, so let me take you back to your first course on calculus, or the last time you taught calculus, complex analysis. So the Cauchy-Riemann relations are the following. So if you've got two real functions, j superscript x and j superscript t, then I can form a complex function. And this is differentiable in the following, if the following two relations hold, the Cauchy-Riemann relations, and there are two of them. And they look like this. And if you just switch to this standard notation, x plus it is z, then you can just write them in this form down here. So the first relation, this one, is current conservation. And the second one isn't current conservation. It's a sort of rotation-free condition for these functions. Okay. What's that? Oh no, it's a rotation-free, so curl-free. The curl is 0, essentially. This is, yeah, that's what I meant. So this is like divergence as being equal to 0. And this is like the curl, up to a minus sign, and this is the curl being equal to 0. Okay. So what I want to do is I want to discretize these relations, and there are many ways of discretizing these relations, and so let's look at one particular one. So what I'm going to do is I'm going to define, I'm going to have a lattice, and to start off with, this is just going to be a square lattice. And I'm going to define functions that live on the midpoints of the vertical edges and the midpoints of the horizontal edges in the way I've shown here. So these ones that live on the vertical edges are going to have a bit I'm going to call j superscript t, and the ones that live on the horizontal edges are grade j superscript x. And then I want to think about the discretization of this first Cauchy-Riemann relation. So all you do is you just discretize the derivative in a kind of obvious way. So this term here becomes a difference in the time direction, and this becomes a difference in the space direction. And so I can view a discretization of this as this 4-term relation here. Okay? And I'm calling that D1 for discrete holomorphicity 1. So then I can rewrite this in terms of an integral relation, an analog of the integral around a line integral around a curve being equal to 0 in the following way. So if I define this field J with no superscripts as the bit of the components that live on that particular edge, so on the horizontal edge I have Jx, and on the vertical edge I have Jt. So instead of having Jx plus it here, I just have Jx, and instead of having Jx plus it, I just have ijt. Okay? So I'm sticking in some little factor I. That's another way of looking at it. So if I do that, then this relation just has a really simple form as a discrete integral around an associated plaquette on this lattice. Okay, where these dzis are just the little the complex number increments as I go around anti-clockwise on here. So dz1 is I, this is -1, etc. Okay? And this is just the rewriting of this relation. So this is the kind of integral version of this discrete holomorphicity condition, or D1. And at various times I want to think about it either as a derivative or as an integral, but when you've got discrete complex analysis, there's no real difference between derivatives and integrals, as you can see. Okay. So then, what about the other? Okay, so as I said, this relation is this, it's just a copying of what was on the previous slide. This is a discrete analog of this. And you can play the same trick for the D2, the other discrete holomorphicity condition, which look like this. So if I discretize this, then I get another 4-term relation. But now the 4-term relation is around this dual plaquette. Okay, so this is a kind of plaquette on the dual lattice, and this is a plaquette on the actual lattice. So this looks like a discrete version around here, and this looks like a discrete version around the other ones, the dual ones. And this D1 plus D2, the two conditions together, are what I want to call discrete holomorphicity, because they're the analog of the two Cauchy-Riemann relations. And D1 alone, again, is just current conservation. Any questions at this point? Oh no, so there are two Cauchy-Riemann relations, and if I write them, but on the discrete lattice, I can write one as an integral around one plaquette, and the other one as an integral around the other plaquette. Well, yeah, but it's no theorem. You know, in the analog, it would be Moreira's theorem, but in the discretization, there's no theorem. They're just equivalent directly. There's nothing to prove. They're just equivalent statements. Yeah, that's right. So this is this D1, which is this, and this is this condition around here. Yep. And the D2 is the other one. All right, so what I want to get from a systematic construction is objects that obey D1. That's what I want to do. Okay, so let me tell you how these conserved currents arise in quantum groups and how I can then interpret them in terms of discrete holomorphicity. And to start off with, I'm going to do it in this simple way. I'm going to have a simple square lattice, but then I'm going to refine things a bit, and I'm going to embed my lattice in a way such that it's not square, that I have an angle between different edges. Okay, but to start off with, let's just do a very general construction. Okay, so what I'm looking for is I'm looking for some currents that obey this D1. So that's just the same condition I had before, but I've missed off the superscripts now. So this comes directly from quantum groups, and that's an old result that is described most nicely in the work of Bernard and Felder from 1991. So this is at the sort of similar time to Bernard Leclerc, where they were talking about non-local currents in quantum field theory. There was a parallel paper that did this in lattice models, and this is a very nice paper, so I recommend you to read it. So let me give you an example of how this works. And so let's take the simplest example, the one that's also relevant to the 6 vertex model that I'm going to discuss later on, where the algebra is UQSL2 hat. So UQSL2 hat is, well, it's the deformation of the universal enveloping algebra of the affine SL2 hat, affine SL2, SL2 hat. And it's generated by these Chevalier generators, EI, FI, and TI plus minus 1, and I just has two values, 0 or 1. And it's a quantum group, so it's a quasi-triangular Hopf algebra. In particular, it's a Hopf algebra, so there's a co-algebra structure, which means there's a map from the algebra to the algebra tensor itself. And which obeys certain consistency conditions. And I'm just going to give you a particular choice of this, which is the one I'm going to use, and also just for the FIs. So in this talk, I'm going to think about currents associated with these FIs. Right? So the coproduct is the following. It's FI tensor TI inverse plus the identity tensor FI. So that lives in the algebra tensor algebra. That's a choice. But one of the nice things about the Hopf algebras is there's a unique way of defining the multiple coproduct associated with a map from U to U tensor itself n times. Okay, and that works in the following way. So delta n lives in U tensor itself n times. And it just comes from the simple delta. There's a unique way of getting it. And if you do it, work it out, the coproduct itself is just this. So what you've got is you've got these insertions of these FIs at point J, and then to the right you've got these T inverses. And to the left you've got the identities. So for the n is equal to 2, this just coincides with the previous one. And you have to sum over all insertion points. Okay, so that's the coproduct I'm going to use. And it's nicest to think about this in terms of pictures, and it's simpler, I think. So the picture that I'm going to use for a representation, this is just standard R matrix sort of picture stuff, is that I just have a line with an arrow for my representation of the algebra. And then so this is for the vector space, the module in which the algebra acts. And then the action of this Fi on this vector space is given by this, diagrammatically by this. So I put a little cross on here, and I put a tail, a wiggly tail, with an arrow to the left. And if I want, I can put an I on here to indicate that it's Fi, but I'm going to suppress that. So that's what the Fs look like. The Ts look like this. So I've got two of them. The Ts go all the way across, and T inverses are the same, but with the arrow in the opposite direction. So what's the point of this? Well, it's a nice way of representing lots of relations, and in particular, it's a nice way of representing the coproduct. Because if you write down what I had just before, so here's the previous coproduct. So here I have an Fi and a Ti inverses to the right. So if I write that diagrammatically, here's my Fi, and here are my Ti inverses. I connect them up together, and then I sum over all insertion points. Okay? So that's the picture of delta n, Fi. And then you can play games and write down all other relations in terms of these things as well. So for example, and these look quite nice as well, and once you get used to playing with these, it's a kind of nice way of thinking about quantum groups. So Ti inverse just looks like this. It looks like a kind of unitarity type relation. I can pull a line through another line. And, well, less obvious is this. So this is one of the defining relations of the UQSL2 hat. You know, it's the analog of EI-FI commutation relations for the SL2 hat. So if you think about this picture, I've got a Ti inverse, and then I've got an F, so I'm composing downwards, and then I've got a Ti, and if I can zip them together like this in a consistent way to indicate this. And then this relation just means I can pull this knot tight, and at the expense of pulling out this Q to the minus 2 factor. Okay? And you can play the game of trying to write down what other relations look like in terms of this as well. Okay. So then the most, obvious diagrammatic picture is of the R matrix in this, than we're used to. So the R matrix is a map, or R check is a map from V1 tensor V2 to the other way around. And you always, indicate it like this. And the R matrix commutes with the action of the quantum group, R check, and which is this relation. So it's delta X is in U cross U, okay? And this R check commutes with this when acting on representations. And so it's useful to write how this looks pictorially. So for example, if I choose X is equal to Fi, then delta Fi is this. So the idea is if I do this first and then act with the R matrix, I get these pictures. So here's my Fi tensor Ti inverse. And here's my identity tensor Fi. And then I do the R matrix afterwards. Okay? And that's equivalent to doing the R matrix first. So that's the left-hand side. Doing the R matrix first, so we got the cross first, and then acting with this delta Fi thing. Right? So this is the key relation that makes this all work. It's a four-term relation, and this thing is going to give the current conservation relation. And for Ti, it's even simpler. So delta Ti is Ti inverse Ti inverse. So that means so this product is just this composition here, and I can do it either before or after the R matrix, and it doesn't make any difference. So I've kind of got local insertions, which are these crosses, and they're attached to tails. And the tail I can move through any vertex. So then you can kind of scale this up, and you can look at, so now I take the monodromy matrix, which is a product of R matrices, and I can embed these insertions into the monodromy matrix in this way. So I have, so here I've got that 4-term relation around this vertex here, but I've got a bunch of other things attached to it. But those other things don't affect the validity of this local relation. So I've got, around this point here, I've got this 4-term relation, and I've just attached the tail everywhere else. And so what this gives me is a 4-term relation for insertions around this vertex here. And that's equal to 0. So I've just taken everything to the left-hand side and set it equal to 0. Okay, so then if I denote this Fi insertion defined diagrammatically by this, by Jixt, then this 4-term relation looks like this, which in a sense is almost the end of the story. It's D1. The rest is details. So this is the origin of these conserved charges. So I teach both physics and mathematics, and the physicists, I always tell the difference between physics and mathematics is that in mathematics, in physics you manipulate letters, and in mathematics you have to say what these letters act from to. And that's basically the difference between physics and mathematics. So I should be a bit careful. So these, if I want to view them as operators acting on this tensor product space, then they're just this operator that includes all these local R matrix factors and includes these insertions here. Okay, so that's one way to think of these things. I can think of them as operators acting on this n+1 fold space. So they act in the same space as the monodromy matrix. So this is a kind of modified monodromy matrix. But I can also view them as, the other way that I want to sometimes view them is I want to view them as relations between expectation values for insertions on a 2-dimensional lattice. So I think about a partition function with an insertion at a particular point on this lattice, and then and I can then have the tail wiggling any way I like in this lattice to the end, but then I still have this 4-term relation around here. So sometimes I want to think of these as, particularly if I've got a bent tail, as relations between expectation values of such local insertions on a lattice, on a 2-dimensional lattice. Okay? What's that? Sorry? Yeah. Yeah, yes. So, well, not quite from the Yang-Baxter equation, but from the commutation of the R matrix with the quantum group element gives me this relation. Well, the Yang-Baxter is RRR is RRR, but no, of course it implies Yang-Baxter, yeah. So this is the linear relation that implies the Yang-Baxter relation, yeah. So from that, yes, that's right, yes. Well, so the current conservation is the linear relation. The Yang-Baxter equation is the cubic relation. So this is the yeah. Yeah. Yes, that's right. But I want to view it in the other direction. I want to view the underlying structure is the quantum group that has linear relations that implies Yang-Baxter. That's the philosophy. And the linear relations are the conserved currents. That's the idea. Yeah. So I'm not saying anything deep. All I'm saying is, I want to think of this as the fundamental relation, and that implies Yang-Baxter, and that's the philosophy of the quantum groups approach. That's what I'm saying. So, but this is, yeah, that, yeah, yeah. So the currents are just. So I take. Yeah. So all I do is I act. Okay, so this is, you can view this as an algebraic relation. Now I think about how this algebraic relation looks like on a tensor product of representations. And if I do that, I get the monodromy matrix coming in from this bit, and I get the currents coming in from this bit. Okay? Well, the mono... I'm not quite sure what you mean. Yes. Well, in the sense that the conserved charges are a logarithmic derivative of the monodromy matrix, but this current is a generating function for those currents. Yeah. Yeah. Yes. I'm not sure that is your question, but are you happy? Yeah, okay. Okay, so this relation is, so these are non-local currents, and I have a 4-term relation. And it comes directly from constant groups. And that's the observation of Bernard and Felder. Okay, so let me give you an example in terms of the 6 vertex model, maybe it'll become a bit clearer. And also I want to refine this slightly. So instead of having the 90-degree embedding, I want to embed this into the complex plane with an angle that's not equal to 90 degrees. So we've seen this before. This is just the UQSL2 hat. I've changed to L here so not to be confused with I. And now I think about a particular representation. The previous thing was kind of representation theory independent. I could have taken any representation V I wanted. But now I want to specify what this representation is, and I take the 2-dimensional evaluation representation. And all that means is that my generators look like this. Okay. So what's lambda? Lambda is just the parameter that enters the representation. And this, so the T's look like this, and this eta, well, eta is just related to the Q of UQSL2 hat in this way. Sometimes I use Q and sometimes I use eta. And as we've seen, this is the coproduct. Okay, so now, well, if I do write down the R matrix associated with 2 of these representations, I get the 6 vertex R matrix that is just this. And I use the notation SH as an abbreviation for Seinch throughout this. And now I want to think about embedding this into the complex plane. Okay, so. And then I'm going to interpret, the point is once I've embedded this into the complex plane in a particular way, I want to view these, I want to interpret these current relations as being D1 relation in the complex plane. Okay? So now I embed this at a non-trivial angle. Okay, so what's going on here? Well, I think about tails coming in at 90 degrees here, and that's a convenient way of characterizing this angle, which I'm going to call alpha of the Z, and the Z is the embedding point in the complex plane. Okay, so here I've got 4 embedding points in the complex plane, and the angle that this embedding defines is it's alpha Z1 at this point, and here I have alpha Z3, and alpha Z3 is the same as alpha Z1. Okay, so it's the angle of a particular line with respect to the horizontal. And what I want to think about is this angle here. So theta, by definition, is alpha Z1 minus alpha Z2 in this picture. And I can relate this to the spectral parameters, lambda, in the following way. The theta is related to the difference of lambda and lambda prime in the following way. And this relation is fixed by crossing symmetry. So crossing symmetry is this relation down here. So this is the crossing parameter of this model. And if I want to interpret this, as we usually do, as crossing is related to the inversion of the direction of one line, okay, then, and I want this to be consistent with my embedding, then this fixes. What's that? Yes, exactly. So the particles go to antiparticles is this bit here, yeah. But if I want to interpret crossing in that way and under the embedding, then this fixes the relationship between the spectral parameters and the angle. Okay? And it fixes it to be this. Okay, so then what I do is the following. So these were my currents. Okay, these I call them JIs, now I'm calling them JLs. So this was the FL current at the embedding point given by Z. And I write Z and Z bar in here because I want to view these in terms of complex analysis. I don't want to think of them as being a function of Z or Z bar alone. I want to think of them as functions of both. Okay. So if I put in this little factor here, alpha Z, then that means that this relation is true around this squished plaquette. Okay, and these are just these angle factors that give the so these DZs depend upon this angle now in the complex plane. So by sticking this little factor in here, automatically this thing automatically embeds D1 with around this squished plaquette. Okay, so now I want to rewrite this in a slightly different way. I want to add and subtract a factor into this exponential here. So S, I'm going to write as 1, this factor I had up here, plus a bit, and then this extra factor here just cancels this bit coming from here, okay? So this was the spectral parameter associated with this insertion point Z. So I've pulled out this factor here, and then I've pushed this factor into here. But the point is, if I push this factor into here, then that exactly removes, it exactly removes this e to the minus lambda factor here, okay? So what it does is it removes the spectral parameter dependence from the current. So if I pull out this factor here and push in this factor here, then this whole thing looks like the following. So phi naught looks like this factor times phi plus with a bunch of these q to the sigma z operators, and phi 1 has a similar factor here. Okay? And this factor now I want to interpret in terms of spin. Because it tells you how, as I change the angle of this tail around the world, the factor I pick up. Okay, so I want to think of this as a spin-like factor. And this spin is 1 plus I eta over pi, so it's related to the value of q for these operators. And it naturally pops out from this spectral parameter dependence and this embedding. So you get a spin, an operator with spin. Okay. So this is a procedure that was carried out for a range of models, and it was carried out by myself and the collaborators we mentioned earlier for dense loop models, dilute loop models, chiral pots, and now trigonometric SOS. And they're all just using the connections of these models with representation theory. So the dense loop models, there's a connection between the 6 vertex model and an ON loop model. So we mapped these currents across under that connection, and we ended up with these non-local operators in the loop models. And you can do it for dilute models, and then you change the algebra. It's A22 is the underlying algebra for the R matrix, and you can do the same. And then we looked at the chiral Potts model. In the chiral Potts model, the algebra is the same, UQSL2 hat, but the representations are different representations. There's cyclic representations at roots of unity. And there are other complications about how the R matrix is written down in terms of Boltzmann weights in that, but that's not what this talk is about. So what I want to talk about more in this talk is the trigonometric SOS model. And in this case, we start off from the 6 vertex model, and we map it across to SOS models using the vertex phase correspondence. So I want to show you what happens to these currents under the vertex phase correspondence. So in all cases, when you do this, you end up with parafermionic fractional spin operators in the model. Parafermionic, because they've got this, they're chiral fractional spin operators, and they're non-local. And in some of these cases, these are known, and some of them are new. So if Q is equal to 1, then eta is equal to 0, and these become spin 1 operators in that. Yeah. Okay, so let me, before I go into the details of this, just tell you about a use of this, because this looks all a bit formal at the moment. So, well, I've mentioned that we can look at loop models and Z and chiral Potts models. So if we look at the massless loop models and the Zamolodchikov-Fateev point of the chiral Potts, which is the Zn model, then we get parafermions out, and these coincide with existing constructions of parafermions in these models. What's that? Yes, that's right. So they're the lattice parafermions of Zamolodchikov-Fateev, which have the same properties in the scaling limit as the parafermatic operators in the conformal field theory. What about the massive case? Well, in the massive case, this is one of the interesting things. So we analyze this most in the chiral Potts, which is actually the most complicated case. But the philosophy is the following. So we end up with this D1 relation that looks like this. And this, as I said, is just a discrete version of this relation. So remember, integration and differentiation are basically the same. So this is a discrete version of this. So now what you do is you take the massive current and you expand it around the massless limit with some correction. And then you can reinterpret this equation in the following way. So this is going to be the derivative of the massless current is going to be some sum over some other currents, which you identify by using the spin you get out. Okay, so you can identify particular currents when you expand this around the conformal point. And then, so this pops out of this automatically, and then we can compare with perturbed conformal field theory. So perturbed conformal field theory is the following. So you take the conformal field theory and you add in some massive perturbation in this case, and then the current conservation relation you get is modified in the following way, in perturbed conformal field theory. You pick up a relation of this form, where this operator you get on the right-hand side is something that occurs in the OPE of this current, this chiral field in the conformal field theory with this primary field phi I. Okay? So if you look at this OPE and look at the pole, then you get this chi I, and just a bit of kind of standard manipulation shows that this chi I is then what you expect in here. So we can take our relation that looks like this, our discrete version, and we can compare it with perturbed conformal field theory. So this enables you to identify particular lattice models with particular perturbed conformal field theories. And in doing this, we confirmed an old prediction of Cardy for the relation between the chiral Potts model, the massive chiral Potts model, and as a perturbation of the underlying conformal field theory. And so we found that there were three terms in this relation, and these are the spins of these fields. There was an energy operator, which was this, and then there were two W algebra descendants of the energy operator. Okay, and this was Cardy's prediction that such things, that these were the perturbations, and we confirmed that corresponded to the chiral Potts, and we confirmed it using this. And we also nicely found, one of the nice things about this is you can directly find these lambda i's, the coefficients in here, in terms of the underlying chiral Potts parameters as well. So it's there's a concrete use of these things as well. Okay, so let me go on and talk about trigonometric SOS. So this is, so some people know about this, some people don't, I imagine, in this audience. Probably most people do. Well, there's a vertex phase correspondence that takes the 8 vertex model to elliptic SOS models. So this was in Baxter's 73 papers. And if you take the norm of this elliptic functions to 0, then this gives you a correspondence between the 6 vertex and a trigonometric limit of the SOS models. So let me just quickly run through how that works. So here's the 6 vertex model, the thing I wrote down earlier. And how you connect it to SOS model. So I'm doing it directly in the trigonometric limit. So the connection, the vertex phase correspondence, is you introduce some vector valued functions, psi a, b, where a minus b modulus is 1. Okay? And then they're just very simple functions, they're just exponentials in this trigonometric case. Okay, and then the vertex phase correspondence, it's a one-liner, it's this in one line. so there's a connection between the 6-vertex R matrix and these SOS Boltzmann weights that is looks like this. So this lives in the vector space. C2 tensor C2, so it's in the right space to be acted on by the R matrix, and it looks like this. And I'll draw a picture of this in a minute, which becomes more apparent when I'm talking about. And just to write them down explicitly, in the trigonometric case, they're very simple functions that look like this. Okay. So this language is all a bit old hat these days. People don't talk about SOS models so much. They talk about dynamical Yang-Baxter equation, but they're just exactly the same thing. So the connection is the following. So these face weights, I can write them in terms of a dynamical Yang-Baxter equation in the following way. So if I identify this as with these increments of epsilons here, then the connection is this. So I pick up an R matrix that looks like a vertex model R matrix in the sense of the possible values are here and what lambda is. But you also pick up this dependence upon this top left-hand corner height variable A. Okay? And that's the entire connection between dynamical Boltzmann weights and face weights. And just to convince you, the W obeys the face Yang-Baxter equation, which looks like this, but it's also just the dynamical Yang-Baxter equation. So the face Yang-Baxter equation looks like this. I've written it out. So you can take one of these triangles and you can squares and you can squish it through to the right. So its arrangement looks like this. And if I write that in the dynamical language using this connection, it just comes out to be this, and this is the dynamical Yang-Baxter equation. Okay. Yep. Yes. Yeah, that's right. Yeah. So I think the observation is associated with Felder, I think. Okay, so that's so then let's introduce some diagrammatics for this. It makes it much easier. So my R matrix is just the old R matrix. The size I want to indicate by this. So they depend upon A and B, and they also depend upon the spectral parameter, and they live in this vector space C2, which is associated with this black line here. So they're vector objects. Okay. And my face weight, I've already used it, it's just equal to this. So the advantage of doing this is that then the vertex face correspondence becomes really simple. So I take two of these, so sometimes they're called Baxter intertwiners, together, this side, and then I act with the R matrix, and that's equivalent to having the face weight and then acting with two of these things afterwards, okay? So I can kind of flip over, do a flip, a bit like yesterday's flip, on one of these things and move this over. So that's the vertex face correspondence. And well, it kind of works another way. You can introduce a dual intertwiner, and the dual intertwiner is lives in the dual space, which is just a row vector in this context. So it acts from the C2 to C, and it's just this. And this obeys the following vertex face correspondence, which just looks like the previous one, except now these arrows go in to green lines as opposed to coming out of green lines. Okay, so I can flip from the bottom left or the top right and turn a vertex weight into a face weight. And finally, just because I need it, I need to slightly modify this star of this dual operator and introduce another one, which is a sort of modified version of this that I'm going to indicate diagrammatically by putting a dotted line on here. Okay, then if you do that, you get these inversion relations that are kind of key to making this all work. And it's about taking products of these intertwiners, and there are four possible products you can take. And all of these, you get something like the identity on the right-hand side. So this, if you work it out as an operator, it just lives in, it's a complex number. It's delta BIC. But this particular combination is a map from the vector space to the vector space, etc. Okay? And the thing to note about this is that these look similar, these pictures, but on this one, I fix A and sum over B, whereas on this one, I fix the other side and sum over this side. So I sum over the right side here and fix the left side, and I fix the right side and sum over the left side. That's the difference between the two things. So what's the point of all this? Well, we can map partition functions and correlation functions in one model into the other model. So let's take the dressed partition function. So this is the 6-vertex partition function, and on the boundaries, I dress it with these Yang-Baxter intertwiners. Okay, so I sort of wrap it in these things. And I fix these values of the heights along this edge to be anything I like. Doesn't matter. And now I start peeling off from the top left-hand corner and turning black crosses into green squares. And I can keep doing this from the northeast down. I could also have started from here, but let's do it from here. So I move all these things down. And if I do that, I get to this point. Okay, so I keep doing this again and again and again. And I get this little seam down the left side and the bottom side. But then this seam disappears because of these inversion relations. So if I take this inversion relation, which means I fix this value here, then that gives a delta function between this height variable and this summed over height variable here. And so this disappears. So from the top down to here, I can zip this back up, essentially. Okay, so I get this seam left in, but this seam disappears. And so if I do that, I get that the partition functions of the model are just identical with fixed boundary conditions. Well, this also works. What about correlation functions? This also works for correlation functions. So let me give you about a local insertion in my lattice. So I put some local operator in here. So now things are a bit different because there's an obstruction. So I come from the top right and I come from the bottom left. But at a certain point, I can't keep going because I get this obstruction. So what I end up with is this non-trivial seam that goes from the origin to the boundary. Okay? And this is just a minor technical point. I've decided to put a dash down here because this simplifies this picture down here. It enables me to zip things back up on this section, but that's not important. But the important point is that local operators in the 6-vertex model go into non-local operators in SOS models. And I can modify the boundary up here, and I can move this to the boundary, but I always end up with some seam that goes from the insertion point to the boundary. There's nothing you can do about it. Incidentally, this connection was used by Lashkevich and Bugaya in 1998 to get correlation functions of vertex models. So they wanted correlation functions of the 8-vertex model using the vertex operator approach of the Kyoto school. But the trouble was that there's no free federalization for the 8-vertex model, but there is one for SOS models. So they mapped 8-vertex to SOS, but at the expense that you get these strange defects occurring in the model. But they took care of that, and by doing this, they wrote down exact expressions for correlation functions of the 8-vertex model. Okay, so what about non-local operators? That's what I'm interested in. Well, so this is the kind of insertion that I'm interested in. I have a local insertion, and then I have one of these tails. And for simple tails, well, the same story happens. I just get exactly the same picture that I had before, except I have this wiggly tail coming down here. So non-local operators turn into non-local operators. And that's nice in this case, but what about complicated tails like this? It's by no means obvious that you can use the vertex phase correspondence to map this to something sensible in SOS models. But you can, and it works. So it turns out that you can always use the vertex phase correspondence to push this transformation from vertex models through any arbitrarily complicated tail. Okay, so I put this in this lattice here, and then I start moving around, and then I can use these 4 inversion relations to squish the vertex phase correspondence all the way around any one of these tails. And it's non-trivial, but it works. And in the end, what you end up with is certain rules for non-local insertions in SOS models, given by certain plumbing rules. So this is how to attach these non-local these different components of the SOS current to each other. Okay, so diagrammatically what you get is you get these modified versions of the Chevalier generators. So the modified versions of the Chevalier generators are the original Chevaliers dressed by the vertex phase correspondence. And there are 3 different types depending upon. So this is my dressing of my Fi, and this is my dressing of my tail in one direction and the tail in the other direction. And this one down here is a dots down here as well to make this work. Okay, this is all a bit technical, but but these dressed Chevalier generators obey dressed versions of the algebra, original algebra relations. So, for example, they obey, T, F, T inverse is proportional to F, but I pick up some funny factors. And this is down here. So these are kind of SOS versions of Chevalier generators. So what you end up with doing is you take one, you end up with zipping these things together in a certain way to get a non-local insertion in your SOS model. So this is, I start off from this particular insertion in my vertex model, and I can dress it and then push the vertex phase correspondence through and isolate this particular type of operator, non-local operator. And there are some subtleties about this. And so I always get this, except I have to modify certain corners. It's a slightly funny thing, but you have to end up, if you have a west to a south and you end up with a south to a west, you have to stick in these factors here that depend upon the difference between here and here. But nevertheless, there's a local plumbing rule for SOS non-local operators. Okay, and now I want to interpret this purely as an SOS object. That's the point. So what these, like I say, so just to show you there are certain rules for how to move these SOS insertions around that just come from the ones from the vertex model. So for example, I can take one of these SOS insertions and flip it through an SOS weight. And this just comes from the corresponding relation I had earlier for putting a tail through a vertex weight. So I can undo this, turn this into a pure vertex thing, move it through, and then do it back again. And then you also go to 4-term relations as well, and these are the crucial things. So there's a 4-term relation around SOS weights that looks like this. So this is the analog of my current 4-term current relation. Okay, this is all getting a bit technical, but the point is I can view these JLs, which are these current, so these JLs with these insertions here, so they live on the seams of the SOS model. So what I end up with a non-local current that looks like this. There's a local insertion, which is this capital Fi, and then there are these bunch of these TIs around here. And these live on between the edges of the SOS models. So if I'm careful about what I mean by this, I can just view them as living like this. Okay, and these are just given by these JLs. So it all goes through, and you end up with SOS non-local currents here. And the relationship between the vertex model currents and the face model currents under the vertex phase correspondence is simply this, where I pick up this non-trivial winding factor. It's slightly complicated. But the important thing is that these insertions obey 4-term relations around the plaquettes here. Okay, so I'm almost done. Then I can play the similar trick, and I can write down parafermions. So I now embed at a non-trivial angle. So I now embed at a squished angle here. I embed this into the complex plane. I identify the angle in terms of the spectral parameters of the original vertex model. It's the same story. And I can write down this parafermionic operator as a spin operator times some slightly modified Ji. And these spins are now different. They're 1 and 1 plus 2i eta. So this one is parafermionic. This one is an integer spin operator. So they get modified through this story, and I end up with a DH1 condition down here for purely SOS currents. So if I choose, okay, so if I choose eta as purely imaginary, then it's real, and eta being purely imaginary is what I want in order to identify this with particular conformal filters in it. What's that? Yes, yes. So So these etas are on the section I'm in. They are purely imaginary. Okay. So corresponding to Q living on the unit circle. Okay. So yeah. Okay, I'm kind of done. So what you end up with by this story is quantum group currents lead directly to parafermonic operators obeying discrete holomorphicity conditions in SOS models, trigonometric SOS. So you might think, why have I done this for trigonometric, not elliptic? The trouble is there's no four-term relation for elliptic Chevalier generators because there are no elliptic Chevalier generators. Okay, so I don't have that starting point. So this works in the starting from the sixth vertex model with the underlying quantum group and Chevalier generators and coproduct. That doesn't work for the elliptic model. And we get these paraphonic fields in SOS models, and we're still kind of working through what this perturbed conformal field theory interpretation is. And it's partly because there are different sorts of SOS models, and I want to talk to Paul Pierce about this at some point. And particularly there are, there are ABF models, there are cyclic SOS models, and then there are unrestricted generic SOS models. So depending on the interpretation depends upon which ones of these you identify with. And of course, the elephant in the room is that discrete holomorphicity condition 2 is still missing. It doesn't seem to naturally come out from quantum groups. We tried various things so far, including Kramer's Vanier duality and various other things. Still no obvious origin of DH2, which was part of our motivation in doing this in the first place, but maybe we'll get to that stage in the end. But nevertheless, these things are still useful, I think, both in giving a new algebraic structure within lattice models, these parafermionic operators, and also in this conformal field theory interpretation as well. And I'm going to stop there. Thank you.